So I'll talk about our schedule. Our schedule was shifted one day down. So obviously, this has been the updated pacing guide. So if you notice 10.3, that's today. We're on derivatives of exponential and logarithms. And I'm going to go through that today, just 3.2. Wednesday, we're going to do the derivatives of products and quotients, and then the chain rule the following week, and then the elasticity of demand. If you notice, this next test will be chapters 3 and 4, which is all of this. I was having a very brief conversation, and I was saying that it's always good to do the homework after the lesson. So you have your lesson, you do your homework. Try to have the homework fresh and keep, practicing one or two questions inside the homework, because this section, as you can see, is loaded with concepts. Everything is new. And I'm not saying it's difficult, but it's easy to forget. Okay? So when how can I say this? The majority of the test scores were actually brilliant. They were not bad at all. There were a few casualties, but that's expected. But there's a direct correlation between the students who got 190, that were in that ballpark, and the homework. It's guaranteed, So for the record, you can always email me a question. You could have if you want to have a tutorial session, I'll do one online. I could do a Zoom over the weekend. Anything is available. I'm here every day, half hour before the class starts. You can catch me in the hall. You can catch me here. It doesn't matter. And you have a STEM lab. You do have a STEM lab. As far as the videos go, they're getting good hits, which means that somebody's watching them. Is it you? Do you need to watch them? I don't know. I'm not here to demand of you. I'm here to help you through the class. Is basically my ultimate goal, which is why the recordings, I think, are helpful if we use them. So with that said, you can just keep that in mind, that we do have a packed from 3.2 to 4.6. And yes, I'll do a test review with you, but don't rely on that as the only end-all be-all to prepare. I was surprised with some of the questions that people in this class missed. They're some of the easiest questions we covered in the review. So anyway, like I said, overall, I'm very pleased. I just, you want all your children to do well. That was not my case. I had a few casualties, and I don't like that. So let's fix something. Something didn't work for you last time, fix it. Okay? All right, so let me give you some notes on this. It is quite a bit of notes. New information. Did I hit record on this thing?
I think so.
Good. Well, that's a good thing.
You said you started right spot.
Yeah, perfect. All right, so we're going to start with talking about E of x. If you're familiar with the natural value of e to the x, it's basically 2.71828 repeating.
Yeah.
Something like that.
Mm-hmm.
It's a natural base value that we use. And so it too has a derivative, and it's stubborn. So it's basically a constant. So the derivative of e to the x is, guess what? E to the x. So the derivative of the exponential function is the exponential function itself. So having said that, and I'm not going to go through the proof of it at this moment, but if you'd like, I can. I don't think you need it. Just know that the derivative of e to the x is itself. And so in example 1, we're going to find the derivative of these functions, and we're going to apply the following. So I'll start you with A, where we have f of x is equal to 5e to the x power minus 3x to the 4th power plus 9x plus 16. And so we'll start with that. And if you look at the math of what I'm about to do, you'll see that it's actually very easy to remember. Okay, so again, this will simply be 5e to the x. This will be negative 12x to the third. And then lastly, plus 9. Notice that this constant goes away, goes to 0. And one more time, this is 5 times the derivative of e to the x, which is e to the x, so you end up with the same thing. Okay. In example B, they're giving us the function f of x is equal to negative 7 e to the x plus, I'm sorry, I wrote that wrong. My apologies. 7x to the e power plus 2e to the x power plus e to the second power. And so just to explain something very easy to remember is that this is actually a number. That's why this is stubborn. This is actually a constant. E to the second power is 7.389, which is a constant. So we treat it like a constant. It'll zap out, zero out. So our derivative for this is simply going to be negative 7e x e minus 1 plus 2e to the x power. Remember, you multiply the initial value. That's why e, and always take away the 1 from the exponent, so e net minus 1. Okay, I have 2 more to share with you. Let me see if you can take this away from that. So let's see if you can do c and e. So I have f of x is equal to 4e to the x plus 8x squared plus 7x minus 14. All right, give you a minute to try that one, and then we'll do another example. So this derivative, if you recall in A, very similar. This is going to yield you 4e to the x. Notice it's the same, right? And this will become plus 16x. And then lastly, plus 7. Again, this zaps out. That's just 0. Okay, and part D, or D as an example, if I said to you, find the derivative of this, where I have f of x is equal to x to the 7th power minus x to the 5th power plus e to the 3rd power minus x plus e to the x. Okay, see if you can find that derivative. And again, the hint is look at B. So this first derivative will yield you 7x to the 6th power minus 5x to the 4th power minus 1 plus e to the x. Yep.
Does it matter that e to the x is in the front or in the back, or wherever it's placed? No? Okay.
And remember, in this case, the e to the 3rd power Those are related cousins, right?
Mm-hmm.
E to the second power gives you the 7.389, which is a constant, so it's 0. E to the third is just 2.1828 times to the third power, whatever that gives you. So ignore that. Huh?
Just the talk to the D over the X.
The d over dx of e to the x is equal to e to the x. The derivative of e to the x power is e to the x power. So this is something you need to register in your memory. Everything else we've talked about, right? Because we've talked about differentiation. So you should be comfortable with that. If you're not, again, that's what office hours are for, or if we need extra practice. Okay, so the derivative of the natural log of x. So d over dx of the natural log of x. This is another one that's a staple. This is equal to 1 over x. And I want you to go back to algebra. When we talked about the natural log of a quotient a over b, which is equivalent to the natural log of a minus the natural log of b. You can also think of it in terms of the natural log of a to the power of p also can be rewritten as p times the natural log of a. And the reason for that is, if I give you a question, it reads, let's say I give you, as an example, 3 natural log of x. I want you to remember that you can re-express this as 5, or in this case 3 over x. 3 over x. And this relates back to this rule here. All of this is related. This is why I'm bringing this to your attention. Okay, so more examples how to derive specific functions. If I give you this function and I say to you in example 2, find the derivative. If I give you y equals 3e to the x plus 5 natural log x, can you find the derivative? Find d over dx, or f prime x, or however you want to state this, it's fine. Question? Yeah. So the first derivative, which is all I'm looking for, should simply be 3e to the x plus 5 over x for this piece. And this is the main piece that goes back to those notes.
So the derivative of 5 ln x is 5 over x.
Right, because it's the power of 5 times 1 over x,
Okay.
which is why it becomes 5 over x. Okay, in part B, an example in part B would be if I give you y equals x to the 4th power minus natural log x to the 4th power. Okay, you learned how to differentiate, right? Last time we spoke. So this is y prime equals. What's the differentiated value for the first term?
4x to the third.
4x to the third minus 4 over x. That's it. And again, it goes back to the notes up here. The power times the natural log of a, or whatever it is, which is 1 over x, right? And we learned that up here. All right, 2 more examples of this. Let's see if it clicks. If I give you y equals 10x to the third minus 100 natural log x remember to differentiate. So if we differentiate, do we agree the first term is simply 30x squared?
Yes.
Okay, and the last term?
Minus 100 over
Minus 100 over x,
x.
that's it. Because you just need to go back to this little set of notes right here, where the derivative of natural log x is 1 over x. Okay, and then,
Okay.
what's wrong?
No, we're just like this, I understand this, like last chapter, like graphing bubble, graphing bubble.
Okay, hope this is good. Alright, in example D, yeah, but you have to understand what this means, you know. And you have to understand infinity, you know, negative infinity and all that. Maybe you just need a minute to just sit and talk. I really don't bite. Alright, try that one. Remember, the power rule applies. Bless you. All right, what do we say about this one?
5 over x plus e to the x, because ln b is 1, so it's constant.
Yeah.
So 5 over x plus e over e to the x. All right. So that's nice little practice there. All right, so if you're comfortable with that, that's example 2. Let's talk about example 3, which is all about logarithms. Okay, so this is a little bit of notes. This is on page 191. So here's how this translates. The derivatives of exponential and logarithmic functions and so if we look at the value, if we say for b greater than 0, where b is not equal to 1, so it's greater than 0, not equal to 1, the derivative d over dx of e to the x, we already concluded was equivalent to e to the x. By the same token, d over dx of b to the x, in other words, some base to the x, is equal to that base to the x natural log of that base. Just take it down, take down the pattern, you'll see it. I can say to you as an example, here, let me throw this example at you. If I said to you, find d over dx, so find the first derivative, d over dx, of given g of x is equal to 2 to the x minus 3 to the x. Okay, so this goes back to this little lovely doohickey here. So that derivative, based on this, is going to look like what?
2 to the x ln 2 for the first part.
That's it. minus?
minus, 3, to the x, ln 3.
That's it. That easy enough? Some of this is just a pattern that you're going to get used to, and you'll eventually make sense of it. Okay, the second set of notes that ties similar to this is for b greater than 0 and b not equal to 1. Oh wait, it gets better. And x greater than 0. If I said to you d over dx of natural log x is equal to 1 over x, which we already knew, and given d over dx of log base b x is equivalent to 1 over natural log b times 1 over x.
That's log base b?
Log base b. So an example of this is the following. So if I give you, say function g of x is equal to log base 4x to the 5th. So we begin on this one with g of x is equal, obviously, to log base 4 x to the 5th. We apply power rule, which gives us g of x is equal to 5 times the log base 4 of x. And we conclude that the first derivative is equal to 5 over natural log 4 times 1 over x.
That's times 1 over x?
Yeah. So let me give you these to try. If I say to you, I've got g to the x is equal to x to the 10th power plus 10 to the x power, so if we differentiate, the first derivative is going to be 10x to the 9th, we agree?
Yeah.
Plus
X 10.
10x, yeah, times natural log 10. And that goes back to this example here, example A. A and C are like first cousins. Okay, you have example B right there in front of you, so let's go with D. D says, what if I give you g of x is equal to log base 2x minus 6 log base 5x. Can we agree that the first derivative is equal to 1 over natural log 2
Yeah.
minus 6 over natural log 5, and this is times
1 over x.
1 over x. Obviously, in the word problems that we will do, x is a variable that we're going to plug something into. Throw it in the calculator, you'll have an answer. Okay, natural logs, don't beat yourself up. Natural logs, these are not numbers that are natural to us, I have to say. So we use calculators. We use some sort of technology. All right, so how do you feel so far? Are you worried? You good? You're good so far? Okay. Apparently, I don't know how to staple pages, so. Whee! All right. So now, how do we apply this in business? I have the 3 questions that they provide us in the textbook, all of which is comprehensive. And the first question is price-demand equation. So please make a note that this is all about price-demand model. So this is a price-demand model. So this is some store, they sell blankets. They're saying that they sell X blankets at a price per blanket, but the price demand equation that they give us is given to us, obviously some P equation, and then it says, find the rate of change with respect to the demand when the demand is X number of blankets, etc. Okay, so I'm going to write it down for you. We're going to do this together. Hang tight. So an internet store, who cares? Internet, brick and mortar, doesn't matter. An internet store sells wool blankets for all you care. They're just blankets. If the store sells X blankets, at a price of P dollars per blanket, so at P dollars per blanket, then the price demand equation I'm going to put P dash D. You know it's price demand, or P dash V. Price demand equation is, and they give you the price demand equation where P is equal to 350 times 0.999 raised to the exponent x. They want to find the rate of change of price with respect to demand when the demand is 800 blankets. Like I said, they have some substitution of some sort. And interpret, which we'll do together. All right, so let's use our equation. Here's what we know. They're giving us the equation right here. So that's our f of x. Our f of x is equal to the price, which is equal to 350 times 0.999 to the x power. So to find the rate of change, we want to know the dp over dx, which in our case, since we have 350 times 0.999 to the x power, and applying that natural log of 0.999, because we know this is how we interpret this. So if that's the case, then now that we've done this, we know that that demand per price over dx is equal to 350 times 0.999 raised to the 800 times that natural log of 0.999. Now please put this in your calculators. I don't care if you use your cell phones or whatever. And tell me what you obtained for that value. Don't be shocked, your answer will be a negative number.
It's 8.572.
Yeah. So we can round it to a loss or a decline of 0.16 cents. So you get negative 0.157 initially. So, yeah. So the interpretation then of this question is simply that when demand is 800 blankets, the price is decreasing. Price is decreasing by 16 cents per blanket. That terrible? Pretty easy, right? But you have to understand this is based on a natural log, so you have to remember how we did this mathematically is the key. So as I remember when we were doing the margin questions, remember marginal cost and marginal price and marginal revenue? We need to remember those marginal questions. All right, let me do, you want one more question? I'll do similar. Who cares what the product is, right? Let's change the numbers. So I'm gonna change this to a different number. Let's make this a new question, and this will be 200 times 0.998 to the x power, and we're changing this to 400 blankets or 400 items of whatever, and the question stops here. Everything else has to do with the other question. So it's the same question, numbers changed. Give that a shot. And tell me your final answer. Okay, you're gonna have to work it out, so please make sure you work it out. I would use my phone. Mm-hmm. That sounds correct. So this would be 200, this would be 0.998, 0.998, this would have to be what up here?
400.
Be 400? Yep, and this should give you approximately negative 0.18. Negative 0.18, so how would you interpret that?
You would interpret that as your
When demand is 400 blankets, the price is decreasing by 18 cents
A
per
blanket.
blanket.
Yep, that's it. So we would change this to 400 to interpret this. When the demand is 400, the price is decreasing by 18 cents per blanket. Okay? All right, let me read to you example 5, which is similar in application. So this one has to do with continuous compound interest. So example 5 is all about continuous compound interest. And in this question, it says an investment of $1,000 earns interest at an annual rate of 4% compounded continuously. Okay, so they were asking us in part A, find the instantaneous rate of change of the amount in the account after 2 years. Oh my goodness. Okay, so there's your question. So what we need to remember is that the setup for this question, because it's in years, we're going to look at A of some time period T is equivalent to the initial principal amount, 1,000 E raised to 0.04 T. You guys remember PERT from algebra? It's basically PERT. Principal amount times E raised to the RT. That's what PERT. Okay. Good. We remember PERT. So we also need to acknowledge that the E to the 0.04 is the equivalent to, so B as a value. If we look at this as the lens, A of T is equal to 1,000 B raised to the T, that the b value in our equation is equal to e to the 0.04. So this little part here is basically our b value. So given that fact, this is just a FYI to know, we know that in this case we have a for the derivative a of t is equal to 1000 b raised to the t times the natural log of b, and that's why you need the translation. This also is equivalent to 1000 e raised to the 0.04 t times the 0.04, which mathematically, remember you're multiplying this times this, so you're going to end up with 40 e raised to the 0.04 t. Since we want 2 years, so they're going to ask us what is the value of 2 years. So you would say a prime 2, first derivative at 2 years, is equivalent to 40 e to the 0.04 times 2 as an exponent, which, throw it in your calculator. Let's see if we're able to get those numbers. Let's see if we match on the numbers, because this is very important, because order of operations, people. Order of operations. What do you get? 43.33 per year. Per year. So that, all of this is the explanation for part A. So this is just throwing you into where the math comes from, that's all. If you need a minute, I'll give you a minute. The question stem in part B, if you're ready, it says find the instantaneous rate of change of the amount in the account at the time the amount is equal to 2000. So this is as easy as 2000 times 0.04, which should indicate $80 per year. I have a second example I can share with you here. So if you want to try that one, or if you want to talk about this one, we good? Okay, so this is another example of example 5. No worries. Tell me when. Okay, so this is another example. It says basically an investment of $5,000 earns interest at an annual rate of 6% compounded continuously. In part A, they want you to find the instantaneous rate of change of the amount in the account after 3 years. I'll start with part 1. Wait, tell me when you think you have a number. That should help get you started. What'd you get for the next part?
I got 359.
That sounds correct. 359.17
Yeah.
per year. All right. Any questions on that one?
It's essential that we put, we multiply the 5,000 B to the power T times the ln of B, correct?
Yeah, that's why we do this little reminder here.
Okay,
So, yeah.
alright.
All right, part B. So in part B, they want to find the instantaneous rate of change. Rate of change of the amount in the account at the time the amount is equal to $8,000. And that's what it should result in. Okay. Last example is example 6. I really need to learn how to staple pages together. What a mess. What a mess. Okay, in this example, it says there is a model. So example 6, you're given a model for the growth of a sandwich shop franchise. In the model, for the sandwich shop, N of T is equal to negative 765 plus 482 natural log T. Where N of T is the number of locations, this is the number of locations. T0 is, I should call T equal to 0 is indicative of 1980. So when we talk about T equal to 48, we are talking about 2028, right? So if I add 48 to 1980, I'll get 2028, if that makes sense to you. Okay, so they want estimate the number of locations by 2028, round to the nearest integer, and what are your results? So since we're looking for 2028, we're looking for N of 48, correct? And this is equal to negative 765 plus 482 natural log of 48. Okay, and so we find the derivative. So n prime of 48 in this case is going to be equivalent to 482 times 1 over t, which numerically is equivalent to 482 divided by 48, which comes to approximately 10. So the way we interpret it is that in 2028, there will be 1,101 locations, and this number is the result of a growing rate, 10 stores, or 10 locations, let me call it 10 locations per year. And so you obviously you'll throw this into the model. Your initial calculation, by the way, if you're wondering where this came from, I didn't write it down, but that's where that comes from. So this 1,101 locations comes from the original N of 48, just in case you were wondering.